Hello, James Flaten here with the Minnesota Space Grant to talk a little bit about doing simulations for high power rocketry. Simulations can be very useful because they allow you to tell what's going to happen before you actually take the time to build your rocket. So you can use simulation programs to design the rocket, and it will do calculations for you like stability calculations. And then you can also take a design of some sort. We call it a model. Maybe it should be called a simulation model. It's not a physical model rocket, but rather it's a simulation model of perhaps a high power rocket. And then you can put different motors in it and simulate how it will perform. The two pieces of software I'm most familiar with are called OpenRocket and RockSim. And in this video, I will be talking exclusively about OpenRocket. OpenRocket is free, and RockSim costs at least some money. And OpenRocket actually not only does the calculations comparably well, it doesn't have quite all the bells and whistles, that's true, but well, it's free. And it also can read RockSim files. So if you happen to have a simulation model that was made with RockSim, you can read it with OpenRocket. So as shown on the board behind me, OpenRocket saves files in .ork format. RockSim is .rtk format. And so I'm going to make two videos. One is, this video is about introduction to OpenRocket and how to use it to simulate performance and maybe tweak a model if you have a model to start with. The second video will be, what if you don't have a model and you want to draw something completely from scratch? Let me share my screen. So you need to download OpenRocket. It's a free download. So here's where you can download it from. I won't do that because I already have OpenRocket downloaded. And then I need a model. So I went looking for a model online, and I chose to look for Mad Cow Arcus HV, only because that's the first rocket that I ever built, the Mad Cow Arcus rocket. And I found it. So there it is, the 2.6 fiberglass Arcus HV rocket from Mad Cow Rocketry. And excepting for it being out of stock, this is a great rocket. So if I scroll down here, I see a few things. I see its length is 52.5 inches and its weight is about 32 ounces. That's before you put a motor in it. And it looks like it's expected to perform reasonably well with a 30-inch parachute. And if I go down here, I can see assembly instructions. That's handy, but I'm actually going to look at the download RockSim file. So in other words, the model, the simulation model, is posted for this rocket. So let me click on download RockSim file. Actually, I'm not going to bother because I already downloaded it. That's fine. I already have it on my desktop. Forgot about that. So let me go to the bottom. This little icon, which shows a rocket launching off of some sort of a ball, maybe that's the Earth. That is OpenRocket. Let me open up OpenRocket. And when OpenRocket opens, well, there's nothing there. Basically, it's a space on which you can draw a rocket model. And so I'm going to go File, Open, and then go to my desktop and find the arcus.rkt file, which I already downloaded, and say Open. There it is. It's drawn the rocket in the box. And before actually doing anything with it, I'm going to save as, I'll put it back on my desktop, but I'm going to save it in OpenRocket format. So ORK format. So now I'm proceeding with a version of this model that is native to OpenRocket. Here's what I see looking around. First of all, I see a rocket. It's laying on its side. It has a nose cone. It has an upper section. It has a coupler tube. It has a lower section. It has fins. And the CG is marked right here. Watch this. Keep your eye on this. And also the CP, the center of gravity. That's the balance point gravitationally, and the center of pressure, the balance point as far as air forces go. And notice that they're about 2 diameters apart, which is good. So up here is the stability. Right now it's at 2.1 caliper. And that just means that this thing would fly stably, but it doesn't have a motor in it. When I put a motor in it, that will move the center of gravity farther aft and my stability will suffer, but perhaps it'll still be okay. Here I have the ability to look at it from different views. Right now, this is called the side view. Here's the back view. So from the back view, I can clearly see that this model has, well, 4 fins. And also I can see that this model doesn't happen to have any rail buttons or rail guides or launch logs. So the model is not capturing everything that is actually important for the rocket. If I go to the 3D figure, now I can actually see a sort of a transparent version of the rocket. I can spin it, I can drag it around. This allows you to actually do some very nice drawings for reporting and stuff like that. Here's the unfinished version, and then there's the finished version. So the finished version is actually what the rocket would look like, but I would say the unfinished version is probably more useful because here you can see inside the rocket. In fact, let me look inside this rocket. I noticed that there's a nose cone with a shoulder. The coupler section, interestingly enough, apparently does not have a bulk plate on the top, but it does have a bulk plate on the bottom, as the model is currently drawn. This is intended to be a parachute of some sort. I would say that's not located in the right spot. That should be at the bottom of its section. I might fix that later. And then over here, I have the fins, and I have centering rings, and I have a motor tube. So I can see all of these parts. And if I go back to the side view, now I start to understand better what I'm seeing. I'm seeing there's the coupler, there's the bulk plate at the bottom, but no bulk plate at the top. There's the parachute, which perhaps should be slid farther down. There's the motor mount tube, and there's a centering ring here and a centering ring here and 4 fins. And here's a list of the parts. So notice there's a nose cone. There's a lower body tube. You know, that's not correct. If I click on nose cone, it highlights that. If I click on what's called the lower body tube, it highlights what's clearly the upper body tube. So first thing I'm going to do is I'm just going to fix a couple of names here. If I say edit, I can certainly change that name to be more appropriate. Upper body tube, and close. And then there's a coupler that couples the upper and lower body tubes together. There is a lower body tube. Here is the motor mount tube, and it's 29 millimeter. You know, I would rather that was a 38 millimeter motor mount tube just because of the motor I plan to put into this model in a minute. So I'm going to edit that as well. Let me click on edit. And here it tells me a little bit about that motor mount tube, how long it is, what it's made out of, its fiberglass. And I'm going to see if I can find in the pre-select, this allows me to choose from a database different kinds of motor mount tubes. And in particular, I'm interested in a 38 millimeter diameter motor mount tube. So let me just say, okay. And notice that it made the motor mount tube bigger, but now it's 48 inches long. That's not really what I want. That's what it would come from the company, and I would cut it down. So here I can change the length. Let me reduce the length down to, I think it was originally 8 inches. There it is, an 8-inch, 38 millimeter motor mount tube. And here, this tells me what it could be made out of, okay? And so I think I will leave it alone. I'll leave it as vulcanized fiber. That's essentially the same. Oh, no, I'm going to change it to blue tube. There it is, blue tube. And what it will do is it will look up at the library exactly how heavy blue tube is, and it will adjust the weights as necessary. Okay. So, oh yes, let me change the name of that. So that's not called 29 millimeter, it's called 38 millimeter. That's just text. So I didn't look up the name. I have to put the name in, close. And then there's the forward centering ring and the forward. So there's another typo essentially. This one is the aft centering ring, the one toward the back of the rocket. Oops. So let me just change that. And the forward centering ring, and there's fins, and there's a parachute, and there's one bulk plate. Okay, so again, this video is to show how to put motors into a rocket and see how it performs, but also how to tweak the model. And in this case, so far, I've just been tweaking the model. In fact, while I'm at it, I'm going to shift the parachute because it's kind of bothering me. If you put a parachute into the lower section of the rocket, it will naturally slump to the very bottom. And even if you don't push it to the bottom, it will definitely go there once the thing launches. So it's best to place the parachute at the bottom of its section, even when you start your model, so that you get your stability calculations as appropriate as possible. So let me go to the parachute. Let me edit the parachute. I notice it's a 30-inch diameter parachute. That was what was recommended on the website. And here is where I can change the location of the parachute. Notice I can move it around. And so I'm just going to push it down here, more or less close to the bottom. And I'm going to claim that this parachute probably will occupy a little bit more space. So I just increase the length of the parachute as far as how tightly it packs down. And I'll just set it right on top of the motor. That's essentially where the parachute will go, in a protective cloth, for instance, so it doesn't get singed by the explosion from the motor eject. That's fine. But one thing that's actually genuinely missing from this model is any recovery harness, which can be a sizable object and possibly even heavier than the parachute. So I really do want to add some recovery harness. Where? Well, in the lower body tube. This is a single deploy rocket. The pressurization area where the parachute is down here, there's a bulk plate. This entire upper half of the rocket is open for use as a payload bay. If you want to put any avionics or anything else in there, it's not being used for extra parachutes on this particular model. Okay, so in the lower body tube, I want to add one more thing. And the thing I want to add is a shock cord, or for high power rocketry, perhaps call that a recovery harness, a retention harness. And that should be made of tubular nylon, about 11 millimeter tubular nylon. And I want that to be maybe 12 feet long or so. So it was way too short and it was way too lightweight for my taste. But when I make this change, this is going to adjust the weight of the rocket. And I also should say how big I think it will pack down to. Let me just say that that packs down to about 3 inches. And it's maybe about 2.5 inches wide. And notice that it's been drawn here at the very top of the body tube. And so I just am going to slide that down right next to the parachute. Okay, so now I have a parachute and shock cord, and I'm going to close it. There's something slightly weird going on here, and that is that as I put these new components in, it's not actually adjusting anything as far as stability. It's not changing at all the location of the center of mass, center of gravity, as it ought to. And the reason for that is that up here, these anvil icons, they say that these items have been pre-stated and you don't need to calculate them. I'm going to turn off all of those overrides. So here's the body tube. Let me edit that. Let me go to override, and it says the mass is exactly 15.6 ounces and the length is exactly 13 inches, and use these numbers no matter what. I'm just going to turn those off. What this will allow it to do now is calculate the mass based on what I told it about the material, and it probably will do a good job. But now at least the calculations will become live again. So I'm also going to turn off the mass override for the upper body tube. Override off, off. I'm going to turn off the mass override for the nose cone. Actually, both the mass and the center of gravity override for the nose cone. And then there was actually a mass and center of gravity override for the overall rocket. Okay, so it turns out it's true. When you build a rocket, usually there are things in the rocket that are not in the model, especially epoxy and stuff like that. So sometimes you end up with a slightly heavier, maybe slightly lighter rocket than you expected, and you can balance it on your finger and figure out where is the exact center of gravity, and you can override the calculations by the program to force it to use a specific mass and a specific center of gravity. But I think for design purposes in particular, it's good to leave the overrides off, and then you will have live calculations. So I'm going to go to the nose cone. I'm going to the stage actually, and I'm going to edit that. And it said, force the mass to be 32 ounces. Turn that off. Watch down here. See the mass, 30.5 ounces. If I force it to be 32 ounces, now it's 32. But if I turn that off, it estimates it's going to be 30.5. So it thinks it's a little bit light. And then if I turn off the center of gravity, which right now is at 35 inches, over here, see the 35 inches, let me just turn off the override, and now it's down to 32.4 inches. Maybe that's, in fact, possibly more appropriate. Now, watch this. This is the center of gravity, and if I take a component, for instance, if I take that shock cord that I added, recovery harness, and if I drag it around inside of the rocket, so for instance, I move it here, notice how the center of gravity shifts. Basically, this is a piece, a chunk a heavy chunk, in fact, of the rocket, and the center of gravity location will notice when that is not at the same spot. The center of pressure, on the other hand, doesn't move at all, and that's because the center of pressure is only based on what's on the outside of the rocket, and I'm moving around a piece that's on the inside of the rocket. If I wanted the center of pressure to change, I would have to maybe change the fin shape, bigger fins or more fins or something like that. Okay, so here is, I'm going to add one more thing. And that is, at least when I build rockets, I have a tendency to add forged eye bolts, which are actually about 1 ounce a piece. So they're actually kind of chunky. And I'm going to say that this recovery harness would typically be attached to the centering ring below it and the bulk plate above it. So let me add a forged eye bolt. And it won't look like a forged eye bolt. I'm just going to add what's called a mass object. And so I'm going to add the mass object to the I'll put it in as part of the lower body tube. It doesn't matter. This is going to physically be within the lower body tube. So let me just associate it, a mass component, and I'm going to call it forged eye bolt. And I'm going to say that it's 1 ounce. That's a weight, not a mass, actually, but that's okay. And it drew it as a circle right here, and that's not the proper location. So I just need to move it by dragging or by typing. This is, where is it with respect to the top of the section, top of the component? I told it this was part of the lower section of the rocket. So I'm just going to increase that down by 1 inch, down by 2 inches, down by 3 inches. That's about where it would be located. Okay. And when I did that, it made a tiny adjustment. I can even make that 3.5 inches to get it outside of, let's see if that works. Close. Yeah, there it is. Right at the base of the what could have been an avionics bay, right at the base of that bulk plate. Let's fly the rocket. Let's simulate the flight of this rocket. So we've been doing rocket design, and here's our list of parts. Now let's talk about motors. Let's say that I want to fly this on a Cicerone H225 motor, okay? First of all, I have to tell it, of the tubes, there's an upper tube, there's a lower tube, there's an inner tube. Which of them is the motor going to fit in? Which is the motor mount tube? And in fact, it's the model was ready to go. It had already selected this one as the motor mount tube. That's where the motor is going to go. That's fine. So now I say new configuration, and then I say select motor. And here's a lot of motors. In fact, this is only a subset because these are only the Cicerone motors. One could have chosen motors from many companies. I'm interested in Cicerone motors, and I'm also interested in a very specific one, the H225. So I'm going to type H225, and it limits the list down to just one. There it is. I will say OK, and when I say OK, watch two things happen. One is watch that a motor will be drawn in here, and watch that the stability will change from 3.3 to a number less than that because I just added extra weight, 10 ounces approximately, to the tail end of the rocket, bringing the center of gravity aft and hence reducing the static margin. When I hit OK, the motor comes into play. There it is. And notice the stability is down to 1.7. That's still considered healthy. Basically, 1 to 3 is probably good. More than 3 might be a bit overstable. From 1 to 0, that would be marginally stable, and negative, of course, is unstable. I'll consider this OK, 1.7 caliper for my stability. So now let me actually simulate how it would fly on this particular motor by going to Flight Simulations, and then say New Simulation. And it asks me some questions about, well, okay, where are you launching it from? You can even put latitude, longitude in. I usually don't bother. How much wind was there? I think I will leave that at 4.47 miles per hour. That's a light wind, but not unusual, not improper. You could try what happens when it's really windy or what happens when it's really calm. I'm going to leave that alone. This one is important. This is the length of the rod or the rail in our case. And so we use 6-foot rails, so 72 inches. That's the appropriate length. Make sure that that is 72 right there. And then simulate and plot. That just means draw graphs of how high this will go and how fast this will go. The plot is going to be generated with multiple things on the same vertical axis. So right now it's planning to draw altitude versus time, vertical velocity versus time, and vertical acceleration. These are the big three, the typical three. I'm going to add one more. I'm going to add lateral distance. That means how far does it drift? And I say plot. So here's what I've got. First of all, altitude is in red. So the idea is here are the altitude numbers, the scale. And on this motor, this particular rocket goes about just over 3,250 feet, a little tiny bit more than that. It comes over the top, and apparently the parachute doesn't come out. There's the apogee right there, and the parachute doesn't come out until a little bit past apogee. I can probably fix that. But let me leave it alone, and then it comes down at a pretty much a constant rate all the way to the ground, landing at about 150 seconds after it was launched. Notice that in the blue, the vertical velocity, the velocity gets very high. And in this case, I need to read the numbers over here. So this will be vertical velocity in feet per second using these numbers. So apparently it gets to almost or around 700 feet per second top speed. And then, of course, it slows back down. And then it comes down under parachute at a constant negative, slightly negative velocity, maybe coming down at about 20 or so feet per second. We'll see that in a moment, the actual number. Here's the acceleration. This one is harder to read, so harder for me to read, at least. I'm not good with colors. So basically, that's in this light greenish color. It peaks up here when the motor is burning at vertical acceleration in feet per second squared using these numbers, maybe in the vicinity of 650 or so feet per second squared. And then the motor stops burning, and essentially it comes down with zero acceleration all the way down. It's not changing its speed, so the acceleration is zero all the way down. Sometimes the units will be G's. This one happens to have units of feet per second squared. And then lateral distance, that's this yellow curve, and that just tells me that as the thing flies, it drifts farther and farther and farther away, and it might land as much as maybe 800 feet away from me, away from the launch site. So let me close that. Let me close this, and it will put some of these numbers onto a table. So here's what I see. This is called simulation number 2. It says that it comes off the rod at 88.1 feet per second. Two things. You have to get the rod length right so it can do this calculation, and you want to make sure this is at least 45 feet per second so it's going fast enough for the fins to do their job. So 88 feet per second, no problem. That's plenty fast. The apogee is at 3269, and if I reran it, it might give a slightly different value. I think OpenRocket puts a little bit of randomness in some of the calculations. The velocity at deployment, I'm not happy about this, 73.2 feet per second. In other words, it's moving pretty fast, and that was because it went over the top and was on its way down. I need this parachute to come out more exactly at apogee. And so I'll get back to that in a minute. Delay 11.6 seconds from motor burnout to the peak to apogee. So I really should change the motor so it actually goes off at that time. The maximum velocity, maximum acceleration, the time to apogee includes the motor burn, so that's a little bit longer than the delay time by the duration of the motor burn. 150 seconds approximately total flight time, hitting the ground at 23.1 feet per second, which is healthy. For a long time, Tripoli had 25 feet per second as the limit. Shouldn't come down faster than that. Recently, they actually changed that to 35 feet per second. I think 25 feet per second is still a good thing to aspire to. If I change the parachute, it might come down faster or slower if I go bigger or smaller, but this is a healthy number. Let me go back and take a quick look at a couple things. If I go to the parachute and say edit the parachute, I notice that it is not ejecting at apogee, but I want it to come out at exactly at apogee. Okay. And then if I go to the, that's fine, I'll close that. So I adjusted when the parachute comes out. And I'm actually going to adjust the motor a little bit as well. One moment. New configuration. Trying to remember if I can edit the motor. Yes, if I double click on the motor, I can actually edit the delay time up here. It comes with a 14-second delay. Let me change that to 11.6 if it will accept fractional delay. I'm not sure it will. And now let me go and re-simulate it, and hopefully I can at least make this number smaller because it won't go past apogee before it pulls its parachute. So let me just say new simulation. 72 is still here, same wind speed, simulate and plot. It still has these 4 things ready to go. And I plot it. And this looks a little healthier. It's a small difference, but up here, it at least starts the descent at apogee instead of starting to descent after it had already passed the top. So if I were to close that, and close this, I now will get another line. And this is much healthier. Same speed off the rail, but much slower when the parachute comes out. So that means I'm not so likely to rip that parachute to shreds. I want to do, let me just see what happens with some other motors. Okay, so this is an H225 motor. Let me go back to a motor and I'll try a different motor. Let me try an H125 motor. So it's still an H motor, still a similar amount of fuel, but less average thrust. And so I think this will be gentler. It might go as high, depending on the fuel, but it might go as high in a gentler fashion, less acceleration. Let's see if that happens. Okay, so here we go. I have the H125 motor, and I'm going to say new simulation, and I'm going to simulate and plot, and I'm going to plot. And it looks like it goes a very similar altitude, but I think some of the other numbers, in particular the acceleration numbers, are likely to be lower. Let's see if I can see that on my table. Close. Yes, not unexpectedly, this is a less thrusting motor, and so it comes slower off the rail, but it's still healthy. And it goes about the same altitude. But notice that it has significantly lower maximum acceleration. So this will stress the rocket less. And then, of course, it lands at the same rate because that's based on the parachute, and I didn't change the parachute. Just for fun, perhaps do not do this at home, or maybe do not do this with a real rocket. I'm going to put a really serious thrusting motor inside of this rocket. Let me go to select motor, and let me try, I think there is such a thing as an H440. H400, there it is. This is called a Vmax motor. So if I choose a Vmax motor, and I do a flight simulation, so this motor, it has about the same amount of fuel, but it's going to, well, actually it has a bit less. It's lower in the H class as far as total impulse, but more importantly, it has lots more thrust, and so it burns out much faster, and so it will stress the rocket significantly more. Let's find out. Here we go. Oh, it's already done it, but no, it hasn't done it. New simulation, simulate and plot. So there it is, 3,000. Close. Wow. Okay, so here's what I see. First of all, I see that it really scoots out of there, 110 feet per second off the rail. It goes a little bit lower because it was less total impulse, in fact. But notice this huge difference. It's increased the maximum acceleration by a factor of about 4. This is likely to tear your rocket apart. Probably this particular rocket, at least this, it might not be strong enough. The rocket itself might not be strong enough to survive this very high thrusting motor. It's a fiberglass rocket, so it might get away with it. A phenolic rocket for sure, quantum tubing for sure would not get away with this motor. So you have to be thoughtful, and this is where simulation programs can be helpful. Okay, so that's what I've got. One more time, looking at OpenRocket in large part because it's free, but it allows you to tell in advance what your stability is likely to be, and also tell in advance what your performance is likely to be. So if you're aiming for a specific altitude, or you're aiming not to stress the rocket more than such because you know it's not up to snuff for really high accelerations, these kinds of programs can help you. The other thing, which will be covered in the other video, is what if you don't have a model? You just have an idea. Okay, and so how do you start from scratch? I showed you how to tweak components, and I even added a couple, but if you want to start a rocket completely from scratch, for a scratch build, for instance, then you have to grab your nose cone, grab your tubing, and make them fit together, and so that will be covered in a second video.